We have more than, well, again, let's start the final session of the day. We have more than 30 minutes behind. So let's try to compensate this delay. We will have 3 more presentations. The first one will be about architecting the metaverse, a paradigm shift in architecture co-design by Micaela Raposo, Nuno Pereira da Silva, and Sara Eloy. The second one is AI-driven visual generation, generative adversarial neural network, and diffusion models by Pedro Meira-Rodríguez and Vicente López Chao. They are also here. And then advancing architectural visualization, boosting scale and reality with augmented reality by Chul Min Yeum, sorry, and Jason Su. They are also here, at least. Okay, okay. Not the both of them, just one. So I will ask Micaela to come to the table. Yes, and you have the floor. Thank you for your presentations. And as usual, we will have a period for debate and some questions after it. So, Micaela, I will have to put a little bit of pressure on time. We usually don't do this, but we are a little bit late, not too much. In Portuguese terms, this is not too much. We are quite okay in Portuguese terms, but I know that we are not always, not all of us are Portuguese, so I can understand that 40 minutes delay for some could be a lot. For Portuguese, we are not that bad. So, Micaela, please.
Good afternoon, everyone. My name is Micaela Raposo. I'm an architect and also PhD student at the Star Research Center in Lisbon, ISCTE. And today I'll be presenting Architecting the Metaverse, a paradigm shift in architecture co-design. This work explores the metaverse potential as a collaborative design tool in architecture. We emphasize its real-time interactive capabilities and support for participatory design. The integration of the metaverse in architecture has gained growing attention in settings as practice, education, and research. It allows immersive 3D experiences through its ease of use and clarity for inclusive exploration of spatial context, both for designers and lay people. The metaverse added value over other realities as extended reality and virtual reality is the openness of the platforms. It allows real-time collaboration among many stakeholders. The key metaverse features are related to embodiment and interaction. The embodiment comes along with the feeling of presence. The embodiment itself is the perception that the user has on itself, when the feeling of presence is the perception that the user has of being in an environment. The embodiment experience is the experience of controlling our own body in a metaverse through an avatar. And the user feels the body ownership and the virtual and real bodies superimposed. On the other hand, the feeling of presence is the perception of being physically in a virtual environment. External stimuli as tactile sensations enhances the feeling of presence while the user is in the real world. The customization of avatars, for example, the photorealistic ones, add for the participant embodiment and feeling of presence. The interaction within the metaverse for architecture includes options to interact with the environment, on the other hand, and on the other hand, the interaction with other users. For participating in a decision-making process, The metaverse should include features that allows the direct manipulation of the environment and the visible objects. It includes adding, moving, and editing objects. The interaction with users can be verbal, through talking with sound or text, or non-verbal, using gestures and body expressions, and also facial expressions of emotions. Facial expressions are the most powerful social symbol of self. However, it is still complex to be interpreted in virtual environments. Our goal was to explore the potential of the metaverse as a collaborative tool design tool in architecture. For that, we examined metaverse platforms, analyzed their features, and discussed their contribution for architectural design. 9 leading metaverse platforms were analyzed based on the research of Ms. Takidis. And then we made experiences with all of the platforms for analyze their features, focusing on features that are essential for architectural design, such as 3D modeling, the customization tools, interaction capabilities, immersion, and co-presence. At the end, I will present 3 case studies that symbolize diverse architectural research scenarios where metaverse can be a beneficial feature. The platforms we analyzed were Frame VR, Mozilla Hubs, Decentraland, Second Life, VR Chat, Prospect, Meta Horizon Workrooms, Spatial, and Archeo. We analyzed 5 categories: functionalities, avatar customization, verbal and non-verbal communication, and direct manipulation. All platforms include free features, although some of them allow also for a paid subscription for enhanced features. Regarding the functionalities, when all of the platforms allow the creation of a virtual scene based on the platform features and predefined scenarios, only some of them allow the customization of the entire environment with personal imported objects. For architectural design, such a possibility is paramount. Editing objects include deleting, moving, sectioning, changing the color, scaling, rotating. Some of the platforms also allow to insert objects such as images, videos, 3D models, and also web browser screens. Some platforms include features for controlling the light, shadows, and materials, which is very helpful for architectural design. And additionally, the possibility to controlling diverse cameras that differ from the user perspective. Here we highlighted the platforms that allow both first and third person interaction, visualization. All platforms allow for making meetings and presentations. And Meta Workrooms or Horizon Workrooms is the one that is most dedicated to this end. It allows to share contact with the participants and also to create queries for the participants. The use of head-mounted displays to enhance the metaverse experience is also very relevant, and some of the platforms allow to use head-mounted displays. Prospect, Spatial, and Archeo are the ones who allow to use with augmented reality. This is beneficial, for example, when a group of people are working on the same room, physical room, and are interacting with a digital artifact that is placed, for example, on top of a real table, and they are collaborating with each other. Regarding the possibilities for avatar customization, the analyzed platforms have several options. One of the most common features is to use a default avatar, but also the possibility to customize a human avatar or import an avatar customized elsewhere. For customizing with the platform's features, includes possibilities as to customize the gender, ethnicity, the face, the color of the eyes, the mouth, the nose, hair, clothes. Mozilla Hub has also the feature to use the camera as avatar, which means that there is a rectangle where appears the image of our camera if it's turned on. And spatial allows to create avatar from camera. This means that we upload an image of us or take a picture at the moment, and the system creates a representation of an avatar that looks like us. This adds to the participant's embodiment feeling. Regarding verbal communication, most platforms enable textual communication. And another popular feature is the spatial audio, which occurs when the signal depends on the distance that the user is from the other user's sound points. On the other hand, the megaphone is when they are in the same environment, all the participants can listen independently of their location in the scene. The microphone is the traditional audio, as in a video or audio conference, and it's used in prospect and art. Regarding nonverbal communication, some platforms allow to communicate through emojis or emotes. And in some cases, the users can use gestures to express their feelings through the avatar's body movements. Other platforms, on the other way, allow to use gestures only when using a head-mounted display. So the head-mounted display allowed to capture the user's movements and not the avatar body movements. Only Meta seems to enable to use natural facial expressions through its MetaQuest Pro headsets. The platforms that allow to use a Meta avatar allow for facial expressions, and the ones are VR Chat, Meta Workrooms, and Arkio. Also, some platforms allow to identify where the other users are pointing at. This possibility allows us to see where the other are working on, or during a discussion to point to an object to discuss about it. Finally, regarding the direct manipulation, the interaction with the virtual scene using direct manipulation is one of the main features of the metaverse when used for architecture purposes. Most of the platforms analyzed allow to draw and annotate scenes, and also to interact with objects, which includes the possibility of grabbing an object, scaling it, or, for example, sitting on a chair to have this experience in first person. Taking screenshots and making videos are also options possible in some of platforms. And measuring the objects in the scene is helpful for architectural studies, and it's present in Prospect and Arkio. Now I will present 3 different architectural research scenarios. The case studies are research projects held at Ishtar Research Center and illustrate the usefulness of using the metaverse in different research scenarios. The first one is about housing customization through co-design processes. And we are exploring how a digital tool can help inhabitants to co-design their own houses. Such scenario will benefit from the metaverse as the interaction with the environment and the immersive nature of the metaverse are intrinsic to the design process, especially when we are working with different stakeholders that may not be experts in architecture. Most of the features would benefit this experience, and the use of the metaverse for this scenario would allow to, on one hand, to overcome spatial temporal barriers, as the metaverse allowed to different people in different locations to join the same co-design process. Also, the possibility to have interactive experience with the digital artifact or the environment, which allows to also to explore different design solutions, which would be very time consuming if compared with other methods, such as, for example, the traditional method of constructing physical models. Also, the immersive nature of the metaverse allows to have a better understanding of the space, especially for non-experts in architecture. The second example focused on using drones for robotic construction. It explores using virtual environments to simulate the cooperation between drones and human workers to assemble complex construction elements. The metaverse in this case would benefit, as in the other example, to join different stakeholders in the same virtual environment, overcoming, again, spatial temporal barriers. It allows to simulate the cooperation between drones and humans in a safe way, because it's a simulation, a virtual simulation, and also, as in the other case, the possibility to immerse in an environment that allows to better understand complex design structures and processes. The third example is a study on how green streets can promote walkability. And also the social integration of older people in the urban tissue. Part of the methodology was to develop studies with older people where they are confronted with different street designs and assessed them. Compared to other methods, as for example, local observations, the metaverse allows to to manipulate the scene. So we can slightly manipulate different variables to test the impact in the users. It also allows to create scenes that are geographically free, which means we can produce a place that does not exist in reality, and test it how older people would react to this scenario, this environment. And also the multi-user experience is also benefit from the metaverse. Just to conclude, our goal was to explore the potential of metaverse in different architectural design scenarios. The 3 case studies presented allowed to understand how the metaverse can be a beneficial tool for such scenarios. Key metaverse features encompass to simulate the design under development, the feeling of presence, and multi-user experience. Although we identified that Archeo and Prospect were one of the best platforms for, or most promising platforms for architectural co-design, and also Mozilla Hubs. However, their servers were shut down this year in May. Although the potentials of the metaverse, there are also obstacles to overcome, as for example, the level of realism, the internet speed, and the availability of advanced design tools. This is not the last version of the slides. However, the use of the metaverse extends beyond the design and pre-construction phases that we explore in this research. And we advocate that our daily activities can occur in the metaverse, as for example, schools, public services, and places we use in our daily life can occur in the metaverse, and the architects play a crucial role in designing this new holistic world. Thank you very much. I end my presentation with that.
Thank you. Now I'll call Pedro.
Good afternoon. My name is Pedro Meira-Rodríguez, and I am with Dr. Vicente López Chao, the co-author of... Good afternoon. My name is Pedro Meira-Rodríguez, and I am with the Dr. Vicente López Chao, the co-author of the chapter AI-Driven Visual Generation, Generative Adversarial Neural Network, GANs, and Diffusion Models. The aim of this presentation had two sides. On one hand, it shows to establish a general framework to understand the working of some of the most commonly used types of artificial intelligence for visual generation. On the other hand, it tends to observe how these AIs were being used as tools for spatial design and environmental design files. To provide more specific context, I will discuss how this research contributes to my PhD thesis. The proliferation of AI-generated images has raised questions about transparency and ownership. To clarify some of them, my thesis seeks to allow the architects to exert greater control over the creative process using AI-driven design tools and identify the key challenge and opportunity in these emergent files. In the first image, we can see one of Juan Zeng's works focus on integration of GANs as tool for room distribution in homes. In the second one, it's shown a number Nuray's Instagram publication in which use a 3D model image to speed up a render with stable diffusion. To fully leverage these AIs, it's important to understand how they work and delve into the main difference between its type. Firstly, GANs are neural networks introduced in 2014 by Goodfellow. They consist of two elements, the generator, who creates images from random noise, and the discriminator, which evaluates the authenticity of this image. Both components work in an adversarial process to improve the quality of the generated images. The generator proposes a visual output, and the discriminator, by comparing it to the database, tries to determine if the generated image could belong or not to this database. If the discriminator detects the generator image as fake, it uses backpropagation to retrain the generator. However, if the discriminator fails, it learns for future generations. Although their development marked a significant leap in AI research, GANs face challenges such as a long time training process and the risk of system collapse. In recent years, research has continued on possible application of GANs in spatial design with efforts to mitigate these flaws. Among them, works like the ALAIs stood out. ALAIs use pix-to-pix and an air plan as a foundation, stand out for creating a generative room model capable of currently integrating bubble diagram. In a different direction, in 2017, Paswani proposed a new method for processing information, transformers. Transformers solved most of the problems present in GNAs just by getting attention. The key to their function was processing the terms through key vectors and query vectors, which allowed for interpreting input information in a non-sequential way. This is crucial because it allowed each word in the prompt to be related with the most current term instead to the closest one. Thanks to this research, the first text-to-image diffusion model appeared in 2020. These neural networks, now used through software like DALI, Stable Diffusion, or Midjourney, do not rely on adversarial logic. Instead of generator and discriminator, they use forward diffusion and reverse diffusion to generate images. In the first step, image of a specific object are diluted until they become a Gaussian noise. Then the AI attempts to restore the image from this noise, learning noise removal patterns for each requested object. With this training, when generating an images, it starts directly from the noise and predicts the object requested by the user. While they all share common points, it's important to highlight the main difference between the various diffusion models and their method of communication. DALL-E launched in 2021 and integrated into ChatGPT stands out for its accessibility and ease of use. Midjourney, on the other hand, delivers visual powerful results and offers more control without overcomplicating communication. However, its use through Discord and the need of a subscription make it less accessible. Finally, Stable Diffusion is known for being an open source AI with an active community. It offers a much higher degree of control, but the graphic results are lower quality unless the user masters the tool, which increases the learning curve. Regarding communication, the inputs and instructions that user give to the tool can be classified. Regarding communication, the inputs and instructions the user gives to the tool can be classified in two types of variables: persistent variables and complementary variables. The first refers to the values that are necessary for image generation, and the second to the values that provide additional information to the prompt. In the first group, we have the checkpoint, the pre-trained model itself. It uses the main database to generate image and is the main responsible for generate this image. The sampling steps are the number of steps that are used in the noise decoding process. By fixing this parameter into a specific value, it's able to replicate the specific results and the textual prompt, the text typed by the user that describes the object. In the second group, we can find negative prompt, of course, opposite of the positive prompt. It used to specify the elements that should be avoided in the generation. Low-rank adaptation models that complement the generation with small pre-trained specific models. LoRa's can be focused on style, color, shapes, and their influence can be modified easily. And at last, reference image that can be processed based on their style, structure, lines, or depth. Here we can see how an image changes when we modify the weight of LoRa. It's present in a generation adjusts the shapes and materials. However, if its weight is too high, it can negatively influence the plausibility of certain textures, which could reveal the bias of the model. It's important to note that not all these variables are editable or accessible in all generative diffusion models, as seen in the table below. With more variables, a higher level of control can be achieved, but the difficulty of use increase. When comparing research in the field of spatial design related to GANs and diffusion models, two different lines can be observed. The first one is related to GANs, focus on floor plan distribution, almost as a complement to parametric design. This can be seen in the aforementioned work of Mohammad Reza Alai and the research of Ural, who propose a workflow using graph-to-plan with an alignment processor for vectorization. About the diffusion models, studies that explore their application as design instrument focus on their potential to generate inspiring images and renders. In this regard, two papers were particularly revealing. Chang et al. Interviewed different design professionals who use generative AI as daily tool. And although the study did not conclude if there was a specific prompt type that allow greater control over the results, the ability of these models to generate both aesthetic and useful image was valued. In the second, Petrov and Simovic shared the possibility of mid-journey and stable diffusion as visual generators for architecture and compare both programs based in their environmental, formal, and material file to study their application as a tool for vernacular architecture confection. It's clear that generative AI is a powerful tool, but we need to refine its application. We need to delve deeper into understanding how to achieve consistent, creative, and controlled outputs, which is the main goal of my PhD thesis. While this is not part of the communication, we want to take the opportunity to show some advanced or future intentions. In the following generated outputs, syntax based on keywords with a sentence structure and a concatenated processing of phrases have been used. The screenshot corresponds with a preliminary data, but it visualizes how a generation can change by modifying a textual prompt syntax. Even with a small sample, it's evident that keeping the value of the other variables, there are internal similarities and difference in terms of formal variety, lighting, representation, and materials. We believe that continuing to explore in a systematic way will be the key to being able to design a solid workflow that allows AI to become an efficient tool instead of just a black box that is erratically given instructions. Thank you so much for your attention.
Thank you. The last presenter, please.
Last presentation of the day. I'll try to keep it as short as possible so we can all move on. So today I'm going to be presenting you guys advancing architectural visualization by boosting scale and reality with augmented reality. And so really quickly for me, I am an engineer actually by definition. I graduated from the University of Waterloo with my bachelor's of applied science from a program called architectural engineering, which kind of bridges the gap between civil engineering as well with architecture. I'm currently a candidate for my master's of applied science. Also really briefly, this is kind of the lab that I'm a part of, which is called the Computer Vision for Smart Structures. And so we heavily focus on using sort of automation to do like inspections and analysis for existing buildings and bridges. There's also a heavy application nowadays of using drones and AI and using AR and VR to try and do sort of autonomous work in the field and industry as well. And so really quickly before we start the actual presentation itself, I wanted to really run through the inspiration of why I kind of wanted to work on this as kind of my thesis for my master's. And so in architectural engineering, every semester as an undergrad student, we take a design studio. And in our first year, we take a design studio called Structural Design Studio. And you can read the description of the course there, but I want to draw your attention to that last sentence, which says exposure to three-dimensional modeling and model building. And so you can see the students do a very good job, and these are some of the projects from our year of making models that look very accurate and very like realistic to what they might be on site. However, one of the comments that are reoccurring year after year is the fact that students don't feel as if they actually truly understand the scale of these models. They feel sometimes that even though there's a little marker on the side that shows that scale, and they've built it themselves and they understand that there's a humanoid and how that respects with the model itself, they still feel like there is some distance from the actual scale and the reality. Also because you can't typically use all the materials that you're choosing to use for your models. And so this is where augmented reality can come in. And so when we look at the benefits of augmented reality, we kind of look at 4 of these main things. In terms of scale, we're enable the users to experience spatial dimensions as they would appear in the physical space. When we look at reality, it creates this immersive experience where virtual objects blend seamlessly into the real world environment. There's also direct user interaction, which allows users to directly interact with the model, with the environment. And there's also that extra layer of interior to exterior perspective, which you don't really get when you're doing renderings, for example, because you can't really simulate the real world as the real world. There's always that element of virtualness. Now, when we look at the 2 main topics here, we're looking at scale and reality, and how we've loosely defined them is for scale is how accurately can the user perceive the size and the mass of the design. And when we look at reality, we're looking at how tangible does the design actually feel. And so through the literature, some of the early gaps and opportunities that we looked at are in the early design phases, there are existing applications that use AR. A lot of them, however, focus either on, for example, small scale tabletop models, which people can use their phones, for example, and walk around a table to visualize, for example, a building. Or there's large scale visualizations, but they actually occur ex situ or off site in either like a warehouse or a white box. And so you don't get that reality of the real world environment the building is being put into. And so when we look at our sort of potential for this project, we're looking at how can we use AR to directly project these models into the physical environment they're actually being built in, and helping the users understand that spatial relationship and feel as if they're actually within that building. And so these are our 3 main project objectives. And so we're trying to study the potential of implementing AR and how can we enhance it with architectural visualization. We're trying to improve the understanding and scale and realism by leveraging models, lighting, shadow, and occlusion. And ultimately, we're trying to demonstrate how AR can be utilized to support a more immersive and intuitive understanding of architectural design. And so in order to complete this, we're looking at 4 specific modules in this scenario. And the 4 modules are the model itself, occlusion, lighting, and shadow. So starting off with the model, let's just quickly run through the prior of what actually happens within that course. And so in the class, we're expected to make both a rendered model, and please excuse the poor rendering, this is a first-year engineering student, we don't really know what we're doing. And also we have to make a physical model. And so these are the 2 representations of the project in the class. Now, in order to execute sort of the model at a high level, we need to select a few things. The first thing we need to select is a modeling software. You can use whatever you like. In our case, we chose Rhinoceros because that's the program that we get introduced in for that class. And what all you're doing is simply creating your model and you're exporting it as an OBJ from that software. The next thing you need to select is you need to select a game engine. So think about the difference think about the pipeline between a model to a final render. You need a rendering software. And in this case, it's the same situation where between the model and being able to place it in AR, you need a game engine to help run that software. And so in this case, we've chosen to use Unity because Unity is a very simple, free to use tool for many users, for all systems of operation. And it's also very easy to learn because it's not C++, it's C#. And so it's a much easier language. And then the main thing for the model is the fact that we need to apply materials into the model. And so there's 2 primary things that we need to focus on when we're applying materials. The first being on the top there, the texturing, sorry, the actual layering of the material. And so you can see there on the left, you have the wood actually following the grain of how wood would be in the real world. Whereas on the right side, you have the right beam there following reality. However, the left beam there is going vertically up, which is against the grain of what wood would actually typically be like in that type of a scenario. The other thing that we have to look at is how we're actually applying the material mapping. And so on the left here, we have simply just an image of concrete placed onto the virtual object. But then on the right, we're using other types of mapping, such as normal, like the normal map, the base map, the occlusion map, and all of those help add in more reality because they're doing things like self-shadowing, self-lighting, and so on and so forth. And so for this project specifically, the left there is the model in Rhino with the layers all set based off the materials. And the model on the right is with all the materials added, and that will be later on used for our actual demonstration. And so when we look at the relationship between scale and reality as with regards to the model, in order for scale to be realistic, we need to have accurate texture mapping, and we also want to ensure that the model is built to the real world scale. In terms of reality, we're looking at accurate material generation. Next up, moving to occlusion. Before we talk about occlusion itself, we should talk about the platform that this application was developed for. And in this case, we're using an iPhone or the Apple operating system. Again, with some of the other things, it's very compatible with Unity and it has lots of SDKs already pre-built in. And the key function here is the fact that it has an inbuilt LiDAR sensor that provides an accurate reading within a 5-meter range. This accurate reading is also continuously updated as you continue to scan other areas. And so the execution of the occlusion is very straightforward. You need a material that is invisible, however, is still considered a solid surface within the game. What this then allows is the game recognizes the material is there. However, you don't see it in the virtual world. You only see it in the real world. And so in our case, we've used the material that's sourced from DevDunk Studio. And here's that example of how the occlusion looks in AR. So on the left there, or in this scene, the paper bag is supposed to be in the foreground. On the left, the virtual object sits actually in front of the paper bag while it sits where it's supposed to in the photo on the right. So when you look at the photo on the left, because of how our perception of depth works, because the cube is in front of the paper bag and we might understand the size of the paper bag, we might start to think that, well, the virtual cube is actually bigger than it is, which in this case it isn't, right? Because it's actually located behind. And so when you do occlusion correctly, it gives the correct sense of scale as well. And so that's reiterated here with the fact that scale and occlusion are hand in hand because of how we perceive objects. And in terms of reality, without occlusion, you don't have a realistic augmented reality application. Next up, we look at lighting. And so for lighting, again, we have to draw some of the features from the iPhone, which is also why an iPhone was chosen, because it's very easy to just draw your longitude, your latitude, your time, your date. And all of these are required to then calculate your sun's location, but also to calculate where the sun is with respect to kind of your current location. And so we use Hesper's package in this case, which helps us both render light color because this color of the sun changes. Well, the color of the sun doesn't change, but the color that's emitted from the sun changes throughout the day. And it also helps us to calculate the location of the sun. However, one of the issues that we ran into just using the package was that it assumes that in Unity, north will always be game north. However, when you initialize an application on your phone, your north is actually with respect to the direction you're facing your phone. And so a quick realignment of your phone's north to game north will help solve that issue. And so when we look at lighting, the first one we're going to look at is just the color based off the time of day. You have dawn, you have solar noon, and you have dusk, and you can see that the colors are varied depending on what it is. And next up, you have with respect to the sun's location. And so you can see the one on the left has an arbitrary location of the sun, and it doesn't actually match that cardboard box there on the right. The top side is very light, like the one on like the virtual object. However, the dark shadows on the right, the dark shadows on the virtual object don't match the one in the box. Whereas on the right image, they actually do match. And you can see that gives it that real that sense of reality when it comes to it. And so when we look at it, scale itself, when you have incorrect lighting, it kind of affects the user's depth and perception of the scale. And then when we look at reality, well, we're giving it an accurate location, and we're also giving it the accurate color that it needs. And last but not least, we have shadow. And so the shadow is really just set up through Unity. You have to set up the three main properties. Render distance to make sure that you actually render in your entire shadow, no matter where you are with respect to the model. You need to worry about the cascade count, which essentially gives you a realistic feathered edged shadow. And then you also need to worry about soft shadows, which prevents the idea of having like harsh shadows intermittently. And again, the occlusion material from DevDunks, in this case, needs to also be able to receive and cast shadows, because even though it isn't visible, because that object exists in the real world, it might still affect the object you're placing in. And so if a shadow lands on it, or if your virtual object is casting a shadow on an object, you need to be able to see that. And so here's a quick example of just render distance. On the left, we have an incorrect one set. On the right, we have a correct distance set. And then here's an example of actually showing a shadow on a ground plane. And so on the left, we have a virtual object that isn't being affected by the real world lighting. But then on the right, it actually is being affected. And you can see that shadow matching the shadow of the water bottle next to it. And so when we look at it, the relationship scale, the render distance may not render the entire shadow, which may cause your model to feel smaller or larger depending. And in terms of reality, it casts the shadow in the same manner as adjacent objects. And so you feel as if the object belongs. And so for the demonstration, we selected a location for my pavilion at Waterloo Park. You can see some of the site elevations. You can also see where the sun is located currently with respect. And again, we're using this model to actually perform the demonstration. And so with time, I won't show the walkthrough video here, but then we can go through the photos. So this is sort of the exterior shot, just a general shot of the model itself. Next up, you can look at sort of what it looks like from the interior outside. You can see that like you can see the real world, but also walk through and visualize what's actually happening. When you look at occlusion, so this is an example where like you have this rock that's farther in the distance, it's kind of lower down. And so you're taking that photo behind it. And because of the way that occlusion works, you don't see the parts that are actually covered, which makes it more realistic. In regards to lighting, if you go back and reference this with the elevation images, you can see that the parts of the building that should be lit up based off of where the sun's location is light up. And you have the darker sides where it doesn't. And then when you look at the shadow, in the photo on the left there, you can see exactly where the sun is coming up from, right? Sort of there in the middle of the image. It's shining directly onto the model, and that model is casting a shadow directly onto the ground there. And again, also you can see the model casting shadows on itself, which is another thing that makes it even more realistic. And so when we look to summarize, here's the list of everything that affects the scale. Here's a list of everything that reflected reality. And thank you for listening to the presentation.
I invite the other presenters to come to the table for a period of debate. Join us, please. Thank you. I wonder if anyone wants to start. No? Well, I will start to give you time to think about some questions. I will start with some remarks regarding the first presentation. It's a topic that I'm really interested in because all the development regarding virtual reality and augmented reality, and in this framework of co-design, they, in my perspective, they really address the co part of the word, co-design. And regarding the design, I have some questions. The first one is, what you put in your presentation is structured on the feedback that we, as individuals, as a body, have within the space. I wonder what about the space feedback? regarding to us? How do you input that space feedback on the perception that the tools based on virtual reality and augmented reality you are processing on? So that is something that I would like you to elaborate a little bit more if you can, because I think that the interaction that we establish with space, it's a two-way relation. It's of course what we build on that relation, but also the feedback that the space give to us. So that is a topic that I didn't check in quite a robust way in your presentation. So I would like you to elaborate a little bit more about that. Regarding the second presentation, I found it very interesting to understand the way you were assembling the the way the machine learn about image, and from that step, how the next one is going to process the image to be created, right? So I would like to go a little bit with a topic that Professor Funkling likes a lot. It's about semantics. And I would like to ask you, in the creation of image that we as architects process, there are a part of, how do you say significação? Meaning, yes. There's a part of meaning that it's embedded in the image that we produce. So my question for you is, if you, in the research that you are developing, if you are going to consider this layer of not a visual thing about the image, but the meaningful of the image. And if you are, how? That's even tougher. And finally, the final presentation. In line with the previous one, I think it was also interesting to understand this effort to bring virtual reality and augmented reality to reality. I found it very curious, that kind of effort. But in a way, again, it was a little bit more about the perspective that we have as an individual. Although you said you talk about shadow and the sun, etc. But I guess that the experience that we have of the space, it's a more embodied one, for instance, textures and stuff like that. So I wonder if in the development of your research, you are wondering to add that sort of layers of a more embedded experience of the places that you can put on this effort to bring virtual reality and augmented reality more close to reality. And those were the three questions that I have for you.
Thank you. In fact, the question you posed is an interesting topic to think about because when we are in an environment and we are, for example, modeling something with the features that these metaverse tools allow us to do, if we are modeling a 3D object, for example, a small 3D object, the object itself is responding to what we are doing, to the user input. However, if you are inside an environment, as in virtual reality, it has also a little bit to do with what you were talking about, the lightning and the shadows. So if, for example, I am in a space, in a closed space, and I try to open a window in this space, we have to process this. Yeah, exactly. Exactly. Yes, we had not just the lightning, but the wind. There is a bunch of experiences that the user have from the environment that should be represented in this virtual environment. And as for example, in augmented reality, the things should be previously prepared. So when I'm with a tablet, for example, a mobile device, I can read some marker or something that would allow me to see the virtual element superimposed in the reality. In the virtual environment, we are inside the object, not seeing from outside. So maybe generative design can help us in that sense. So like changing some feature in the environment should be automatically refreshed and provide these experiences, the lightning, the wind, etc. So it really is a complex thing to envision and to address. Yes.
Thank you. Okay. I think the point is that the AI must be a tool. I mean, this meaning must be in the hand of the architect. We must control the result. Uh, to do it, the question is that delve in how to use these variables to don't let the diffusion model to just generate a beautiful image. Instead of that, we must iterate the different layers, values of these variables to see if by this iterating how we can transform these tools, o sea, these technologies in tools. We should see, for example, how can we use these tools in different processes. For example, it could be used for the first iteration, use it, the image as inspiration, for example, or in at this point in which we have, for example, a 3D model, we could use these diffusion models to speed up a render, for example. The point is that we must keep working and study how to use these tools and transform in a really useful tools, not just this black box which give us a beautiful image and is just this, a beautiful image. The point is that keep working on this iterative process. Will be always a iterative process, but the point is to reach this moment in which we know how to use these tools in a way that provide us a useful start point. I mean, if we want render of some type, for example, start using some values, some layers, some specific reference image and process in a specific way. Start knowing how to use these tools in an efficient way, and to let this meaning in the hand of the architect and not in the diffusion model. I think that's the point. Mhm. Mhm.
We are telling regarding the moment that we are now
Mhm.
how to bring all new language for when I make this new of this field.
Thank you. It's a really tough question because you can only ever get so. Only you can only ever get so real with augmented reality because we don't have obviously on our hand while touching something virtual. One of the things that we have been thinking of and kind of like progressing forward is going from the iPhone into a full headset instead. And so using, for example, the Apple Vision Pro, and then incorporating then like avatar features. So for example, like your arms, your hands, and like your fingers especially, so that we can maybe try and have a method to prevent users from sort of going too far into the model so they can't actually touch into the model. They're kind of like limited to right at the model. They get like this warning where it's like, hey, you're about to go through the model and like actually be in the material. Please put your hand back a bit and try and like avoid that. And I think the other thing that we can do, because we don't have the actual ability to feel textures, is to try and simulate the textures to as accurately as you can. By trying obviously like what we've done now, but you can even further improve that by using more maps and using higher quality images to create those maps. It's really about trying to get it as realistic as possible because you can't actually get to the point right now with technology to be able to feel. And so there is that sort of gap that you can't really solve, but we're trying to solve it in the best method we can. Yeah, it's the challenge right now with augmented reality is you can't feel. And even that's the same with virtual reality, you can't feel. The only way you can feel things is if you have a physical model to scale so that you can feel it. A mock-up, for example, right? Even like a small scale, like 1 to 20, 1 to 10 model that's made and laid out on the table, you can only feel so much of it because it's not to the actual scale of life size. It's a very smaller scale, right? So it is a challenge. It's something that we can try and sort of navigate around to a solution, but there isn't a direct solution because the technologies just aren't currently available in the industry. Anyone? Yeah.
Thank you so much for presentations. It's very interesting. And I have just maybe a simple question about the generative design. I will start that I like the generative design and artificial intelligence and everything, but sometimes I have this fear that while it's not in the best perfect stage now, it can make some damage to our possibility of creation maybe, because when I remember myself, when I started with earlier ArchiCAD drawings, like computers, software, it will like I couldn't make the things that I wanted to make at that time. Now it's better, but before it was quite hard to make what you want and what you can present on a paper. And I think nowadays with generative design, we have also this problem that it's not perfect yet. You cannot still do what you would like to do. And what do you think about it? Do you think it's already we can use it, or should we wait a little bit and wait until it will be better, at least for giving it to students, for example, giving this possibility to explore? Can we explore now, or should we wait? What do you think?
Thank you. Okay. I think CIs could be on one hand a useful tool, but in the other, yeah, a little bit painful. Um, yeah, maybe it's too early to know for sure how it could interact with future designs, but I think that eventually AIs could be will be to be in every design process. I think, in my opinion, that it's fine to start at least knowing how it could work. Mm, but being conscient that these generative technologies have a bias that is not so so simple to type what we want and just take it. I think that yeah, we can let the young architects to start using AI, but like Pinterest, for example, it can be useful as reference. Mm, like cat years ago, I think it will be useful, but first we must know how to incorporate these tools in a design process in the useful way, I think.
Thank you.
Well, now we are officially, even for Portuguese, too late. So tomorrow we will have a artificial intelligence session. We can go on with these topics because I would have 2 more questions for you, but tomorrow I will do it. So I guess now we have port wine waiting for us. So between port wine and artificial intelligence, for now, I think port wine will win. Tomorrow, artificial intelligence will win for sure, but for now, port wine. Thank you. And great job. And you are all invited to the port wine downstairs.